Deep learning models utilize artificial neural networks inspired by the biological architecture of the human brain. We build these systems to mimic the brain's immense computational density and its ability to process complex information. This shallow neural network has only one hidden layer between input and output, establishing a baseline of low computational capacity. Transitioning to a deep architecture changes the scale entirely. Stacking multiple hidden layers creates an exponential increase in interconnected weights. The network learns by iteratively passing data through these layers. Through forward and backward propagation, it calculates its error and makes microscopic adjustments to thousands or even millions of interconnecting weights to minimize the loss function. This deep architecture provides immense representational power. With enough nodes and precisely tuned weights, the network possesses the mathematical capacity to map almost any complex pattern presented to it. However, this high degree of freedom introduces a specific vulnerability. Because the network can fit data with such high precision, it risks losing the distinction between the core behavior of a system and the random noise surrounding it. Fitting a model perfectly to a known set of training data does not mean it has learned how to solve the problem. The true test of an algorithm is its ability to make accurate predictions on unseen data. This chart tracks model performance. A deep network can easily adjust its weights until its training error drops towards zero. But when we feed that same perfect model unseen test data, the error rate suddenly spikes. This mathematical failure is overfitting. A model overfits if an alternative hypothesis performs worse on training data, but produces fewer errors on test data. The model hasn't learned general behavior. It rigidly maps random noise and specific anomalies. Statistical noise is entirely unique to the specific batch of data you train on. An unconstrained network effectively uses its capacity to memorize the training set. This results in a system that cannot translate its internal logic to a new environment. To address this memorization problem, we have to look past the macro network and examine the microscopic mechanics of a single node. This diagram outlines a single artificial neuron. The variables adjusted are the weights, labeled W, applied to incoming signals before the summing junction. In these networks, overfitting leaves a clear physical symptom, assigning excessively large mathematical values to specific individual weights. A mathematically bloated weight completely dominates the calculation. The specific input it connects to now dictates the behavior of the entire neuron, making the system hypersensitive. Because of this hypersensitivity, microscopic changes in the input data, like a tiny fragment of statistical noise, get multiplied by that massive weight. This triggers a massive, erratic shift in the final calculated output. We don't solve this by deleting physical nodes from the architecture. We solve it by mathematically restricting the size of these weights. We achieve this restriction through regularization. Regularization is any deliberate modification we make to the learning algorithm to constrain the model. The specific goal of regularization is to reduce the generalization error on unseen test data, even if doing so intentionally increases the error on our training data.
We do this by injecting the parameter norm penalty, represented by omega, directly into the loss function. Injecting this penalty changes the network's objective. It is no longer evaluated solely on how perfectly it matches the training data. It is now actively penalized for building a heavy, complex mathematical architecture. The alpha variable multiplied against omega is the regularization rate. It is an additional hyperparameter that acts as a dial, controlling exactly how strictly the penalty is enforced. To reach the lowest possible value for this new loss function, the optimization algorithm must now find a balance where weight magnitudes are kept low, even as the model tries to maximize training accuracy. In deep learning architecture, the parameter norm penalty typically takes one of two specific mathematical forms, L1 or L2 regularization. The first is L1 regularization, also known as lasso regression, which calculates its penalty using the absolute value of the model's weights. Because absolute value scales linearly, the L1 penalty takes less important parameters and forces them to absolute zero. This effect, called parameter shrinkage, acts as an automatic feature selection tool, permanently deleting irrelevant variables to create a sparse, streamlined model. L2 regularization, also known as weight decay, operates differently. It calculates its penalty using the squared value of the weights.
Squaring the weights severely punishes the massive, hypersensitive outlier values, but the math naturally prevents it from pushing any single weight completely to zero. L1 aggressively prunes specific features out of the network entirely. L2 keeps all the features, but mathematically dampens the volume of the entire interconnected system. Both methods solve the hypersensitivity problem. They maintain the variables necessary to track complex data while heavily restricting their functional magnitude. Setting the alpha hyperparameter correctly is a delicate process. It acts as a strict governor on the network, and applying too much pressure locks the system down. If the alpha value is set too high, the resulting parameter shrinkage strips away too much of the model's capacity. This leads to underfitting. An underfit model is just overly simplistic. It mathematically lacks the complexity required to learn the patterns in the training data, rendering it completely incapable of making useful predictions. Setting alpha too low removes the constraint entirely. The network returns to its unconstrained behavior, once again over-prioritizing the unique noise of the training data. Discovering the exact mathematical balance requires processing a separate tuning set. Techniques like cross-validation are used to constantly verify the model's predictive power against fresh data. Look at the dense architecture of a deep feed-forward network one final time. We build these deep structures to provide raw capacity. However, allowing that immense capacity to blindly minimize training error at any cost results in the model memorizing noise rather than learning logic. Regularization smooths the chaotic, overfitted decision boundaries back into clean, reliable curves that actually reflect the general behavior of the real world. Predictive intelligence is built on this mathematical trade-off. By binding the network's capacity, we force the system to filter out statistical noise and isolate the signal that actually drives